Okay, now we look at a proof. This is in problem 3. Incidentally, this was problem 4. Should have noted that, but if you're looking at the worksheet, it's going to be pretty obvious which one it is. This is part of, actually this is part of number 2. And it's only part of number 2, so be sure that you understand it. We addressed the first part of number 2, but you know, there are some proofs. And this is only the first one. You should try to do the rest of them. Okay. If one of these 3 vectors, v1, v2, v3, one of 3 vectors in this set is a linear combination of the other 2, we're trying to conclude that there exists a linear combination of the 3 of them, a non-trivial linear combination that's equal to the 0 vector. Now it's a very important kind of central proof here. So if you understand this, you're really doing well. And if you can do the other proofs, you're doing extraordinarily well. So please, if you have time, make the effort. Or if you're in the 285, you really need to make the effort. Okay, so if one of these is a linear combination of the other 2, well, let's see what we can conclude. Well, that means that, well, let's just assume that the one that's a linear combination of the other 2 is v3. Now, I'd wait until the end to comment on this, but I'll say it right now. If v3 isn't the one that's a linear combination of the other 2, then swap whichever vector is listed third with whichever vector is a linear combination of the other 2. And now that vector will be v3, and you know the v3 vector will be will have a different number, and we can proceed. So, and in general, we can say without loss of generality, we can assume it's only one of these vectors because we don't know what order they're listed in anyhow. So just assume though that v3 is the one that's a linear combination of the other 2. If you don't totally understand that, let's just just accept. We're going to assume that v3 is the one that's a linear combination of the other 2. Okay. Well, if that's the case, that means that v3 is a linear combination of v1 and v2. That's a no-brainer. It's a linear combination of the other 2. Well, the other 2 are v1 and v2. And a linear combination is a sum of multiples. So it has to be a linear combination of the other 2, which is v1 and v2. Since it's a sum of multiples, how would we write a sum of multiples of v1 and v2? Well, the way we've done it is c1 v1 plus c2 v2, where c1 and c2 are just numbers. They're the multiples that we add to get v3. So that means then that there exist numbers c1 and c2 such that v3 is c1 v1 plus c2 v2. Okay, well, that's the first thing that we can conclude if we assume that v3 is a linear combination of the other 2. Well, if that's the case, then isn't it true just by algebraic rearrangement that c1 v1 plus c2 v2 minus v3 is 0? And somebody came up with that, and that was very good, because this is kind of unfamiliar type of thinking. It's an unfamiliar mode of doing mathematics, but it's really the way higher mathematics gets done, so we want to get into it. Okay, so do we understand that if v3 is a linear combination of v1 and v2, then there's c1 and c2, such that v3 equals c1 v1 plus c2 v2, so that c1 v1, I didn't write the 1 in my v there, c1 v1 plus c2 v2 minus v3 is going to be equal to 0. It follows immediately from this. Okay, well, then we just have to observe that this is a non-trivial linear combination of the 3 vectors v1, v2, and v3. It's non-trivial. A trivial linear combination would be where 0 times this plus 0 times this plus 0 times this. Naturally, that's 0, and that's trivial. Okay, we're looking for a non-trivial linear combination. And how do we know this linear combination is non-trivial? Well, the coefficient of v3 is -1. So this is of the form c1 v1 plus c2 v2 plus -1 times v3. So that's c1 v1 plus c2 v2 plus c3 v3, with c3 equal to -1. Now, non-trivial linear combination says that at least one of the coefficients is not 0. Okay, well, there it is. Okay, C3 isn't 0. C3 is -1. Okay, no matter what C1 and C2 are, if V3 equals C1 V1 plus C2 V3, then the coefficient of V3 in this sum, that gives you 0, and that's a 0 vector. Knew something was bothering me. Then it has to be like this, okay? Now, there are many possibilities, but you don't have to worry about them. We've proven that there's a non-trivial linear combination of 3 vectors that's equal to 0, assuming that V3 is a linear combination of V1 and V2. Okay. Then, as I said before, the choice of V3 was arbitrary. We could have done the same thing by choosing V2 or V1 to be the linear combination of the other two. But as I said at the beginning, the order of listing is unimportant. So we simply assume we've got them listed so that the third one is a linear combination of the other two. One of them has to be, because that's a hypothesis. That's where you start. Just call that one V3. Okay. Now, you might not grasp every detail of that, but hopefully that gives you enough to go on and prove the other two assertions that you were asked to prove at the end of problem 2.